Until 2017, the gold standard for language translation relied on recurrent neural networks, or RNNs, and a specific variant called long short-term memory models. These systems were built to read text exactly like humans do, one word at a time. Reading sequentially creates a computational bottleneck. The system must calculate the previous hidden state before processing the next word. Waiting on previous calculations prevents parallel training, creating severe memory constraints as sequences lengthen. For engineers trying to build larger language models, this linear processing wall meant that scaling up required an agonizing, expensive amount of time. A team of researchers from Google decided to drop recurrent processing entirely. This diagram shows their proposed solution, the transformer architecture. It removes sequential processing and relies purely on an attention mechanism to draw global dependencies between the inputs and the outputs. By abandoning this step-by-step timeline, the model gains the ability to ingest and process all the data in a sequence at the exact same time. The computation becomes highly parallelized. Instead of reading left to right, the transformer stacks processing operations into a deep vertical pipeline. On the left side of this diagram, an encoder stack of 6 identical layers maps raw input sequences into a mathematical representation. On the right, a matching decoder stack takes that representation and auto-regressively generates the final output sequence. This dual stack structure relies on pointwise feed-forward layers applied to every position identically. Instead, it processes massive amounts of context concurrently, rather than waiting for a linear timeline to catch up. If you are analyzing all the words at once, the system needs a way to figure out how those words to each other without relying on their sequence. This schematic illustrates their solution, scaled dot product attention. The model maps a query vector and a set of key value pairs to an output. It calculates a dot product by multiplying the query of one word against the keys of all other words. This visualization maps the result. The calculated weight provides a precise measurement of relevance between 2 specific words. Here, the system draws a strong contextual link between the verb making and the phrase more difficult, even though they are separated by several other words. By calculating these weights across the entire text simultaneously, the machine instantly maps out the dependencies we interpret as contextual understanding. Running this calculation once gives the model a single perspective on the text, but language is dense, and a single pass might capture grammatical structure while missing emotional tone. As seen in this diagram, the researchers solved this with multi-head attention. They run the attention function in parallel across 8 separate layers, or heads, and combine the results. Think of it like 8 different analysts reviewing the exact same contract simultaneously. One strictly checks the financial figures, another is reviewing the legal liability, and a third checks grammatical errors. Because these 8 processes run at the exact same time, the model extracts entirely different types of meaning from the same input sentence simultaneously, rapidly accelerating its comprehension. There is still one major engineering hurdle. If the system processes every word at exactly the same time, it has no inherent way to know which word came first. To fix this, the team injected positional encodings directly into the input embeddings. They used sine and cosine functions of different frequencies to generate unique values based on a word's position in a sentence. These mathematical frequencies act as a unique, combined wavelength stamp for every individual word before it ever enters a processing layer. With these numerical stamps attached, the model perfects its understanding of distance and relative sequence. The system achieves full structural comprehension without ever reading linearly. To prove this new architecture worked, the team benchmarked the transformer on the highly competitive WMT 2014 translation tasks. They measured accuracy using the standard BLEU score metric. For English to German translation, the model achieved a 28.4 BLEU score, beating all existing models and complex ensembles by over 2 full points. On the English to French task, it set a new single model record, scoring an impressive 41.8. Even more striking was the hardware efficiency. The largest transformer model hit these record-breaking numbers after training for just 3.5 days on 8 GPUs, a tiny fraction of the training costs of the previous best models. Replacing sequential steps with attention meant that training speed was no longer tied to sentence length. This major architectural shift allowed the models to be trained on datasets with millions of examples in days rather than weeks, making the scale of modern language models computationally feasible.